Newton's law of cooling is another application where we use an exponential formula to model a scenario. This is our formula representing Newton's law of cooling. And to understand this formula, let's imagine bringing a hot object into a room that is colder. Cap T is representing the constant temperature of the surrounding medium, essentially the room's temperature. And U sub 0, again this sub 0 meaning initial, or essentially when time is equal to 0, this is the initial temperature of the hot object that is being placed into the room. The dependent variable U evaluated at T is going to be the temperature of the object at time T. And as we've seen in other exponential models, K is going to be the rate that the object cools. However, this formula can also be used when we are bringing a cold object into a warm room where the object would be warming up. It's called Newton's law of cooling, but it actually works for objects that are cooling down or warming up. A slightly counterintuitive fact about Newton's law of cooling is that this rate will always be negative. It's negative if our object is cooling down or if the object is heating up. Now let's briefly discuss why that is. We'll take a hypothetical look at a cooling scenario and at a warming scenario. Let's let the temperature of the surrounding medium, or the room temperature, be 70 degrees. And let's let the temperature of our object be 100 degrees, the scenario where the object is cooling down. In this situation, our formula would turn out to be the cap T, which is the temperature of the surrounding medium, plus the initial temperature of the object minus the room's temperature, and then that's going to be multiplied by e raised to the kt power. Let's just assume the value of k is 0.15, and what we've said is that k needs to be negative, so we'll put a negative on there, and then time t is the independent variable. So in a cooling down scenario, we would end up with 70 plus a positive number, that is the multiplier, on e raised to the negative rate of cooling times the independent variable. So if we envision what this graph might look like, it can be achieved by transforming the e to the t function. Remember, e to the t power is an exponentially increasing function. But this negative 0.15 is going to be a horizontal reflection of that graph. It horizontally reflects it and stretches it out. This 30 vertically stretches it, and this 70 vertically shifts it up. So essentially we have this graph vertically stretched and then shifted up, which means it's going to look something like this. And as you can see, the output temperature is decreasing, which means that the temperature is cooling down to approach the room's temperature. And this was achieved with a negative value of K. Now let's look at the situation where an object would be warming up to the room's temperature, which means that we would bring something cold into this room. So let's say the initial temperature of the object was 40 degrees. In that case, our formula would be 70, which is the room temperature, plus initial temperature minus room temperature would be 40 minus 70, e raised to the, and what we're saying is that this k value would need to be negative, and we're just going to use an arbitrary k here in order to demonstrate our point, and that would be multiplied then by the independent variable. So the formula would turn out to be 70 plus a negative 30, or let's just say 70 minus 30, which is the multiplier on e raised to this negative rate times the independent variable. Now let's think about what this graph must look like. Again, it's a transformation on the graph of e to the t power. E to the t starts off as an exponentially increasing function, but we horizontally flip and stretch that to get e to the negative 0.15t. This is a vertical stretch and a vertical flip. The value 30 is the vertical stretch, but the fact that it's negative causes it to flip vertically. And of course, these are just basic concept drawings, just to give us an idea. And then this is going to be a vertical shift up 70 units so that it has a horizontal asymptote at y is equal to 70. And in order to approach that horizontal asymptote, we'll see that our graph is increasing, which means that the object is warming up to approach the room temperature. And again, we had a k value in our equation that was also negative. So when we're looking at a Newton's law of cooling application, we can expect the value of k to turn out to be negative in both of these scenarios, if the object is cooling down or if the object is warming up.